Hello everybody and welcome to today's lecture for TJML Club and the Advanced Group. So today's lecture we are going to be going over the multi-agent deep deterministic policy gradient algorithm, also known as MADDPG. This name, we call it MADDPG because the entire name is a mouthful to pronounce, and also it looks a bit intimidating, I guess, on first sight, but don't let it, scare you away because it's actually a really interesting, really cool algorithm. Yes, so let's get started. I guess the first thing to go over is this falls under the category of reinforcement learning, and per its name, multi-agent, it concerns itself with the decision-making processes of multiple entities, multiple agents at the same time. So this is not like you have one agent operating in an environment with other foreign agents, and the one agent, you're only concerned about that one agent. No, this is, you're trying to control the decisions of many different agents operating in the same environment. And in addition, these agents are all trying to work towards the same goal. So they're trying to, work together to accomplish, a single goal or a series of goals, right? But the key point here to take away is you want to be able to make decisions so that the agents are able to cooperate, to work together. Yes, and deep deterministic policy gradient. If you guys remember from Dr. Dasgupta's lecture, I think he might have mentioned this, but the DDPG, we're going to go more into this later. So DDPG, deep deterministic policy gradient, it's basically an actor-critic algorithm. And don't worry if these terms are not familiar to you. We're going to be going in depth into this later. But it's an actor-critic algorithm, and basically allows for continuous control. So that's the main takeaway from DDPG. It allows for continuous control, which means you're not choosing a discrete action, right? You're not choosing left or right or up or down. You're choosing something continuous, like a velocity or an angle or a direction. And this is important because in real life, right? If you're trying to implement this reinforcement learning algorithm, this MADDPG, most of your systems in real life are not discrete, right? When you tell a car to steer, you're not like, oh, steer left, steer right. No, you're like, steer left by 30 degrees or 40 degrees, right? So it's really crucial that we are able to get continuous control. And DDPG, the DDPG part of MADDPG, basically lets us do that. Yeah, so where should we start? Let's start off by talking about DDPGs. So we're going to visit the paper for this. Yeah, so this paper, if I remember correctly, it was, written by researchers at DeepMind. And we can glean a lot just from the name, deep deterministic policy gradient, right? So the algorithm combines a DQN with a DPG, a deep Q network with a deterministic policy gradient. And probably the most important part of this is the actor-critic base, right? So if we come down here to the pseudocode for the algorithm, just as a quick overview of actor-critic, basically we have two neural networks, an actor neural network and a critic neural network. And actually, just for a basic problem we can work this on, we can consider the problem of this pendulum, which we want to try to swing upright like this, and we can only control the angular velocity here at the axle of the pendulum. And let's consider this problem in the view of a DDPG, how we would implement a DDPG. So we have two networks. We have an actor network and a critic network. Yeah, so our actor network and our critic network basically work together to, this is once again reinforcement learning. So work together to try to come up with the, best policy for our agent. So in this case, the pendulum. And these are two separate neural networks, but they influence one another. So we can start off with talking about the critic network. And our critic, basically, it takes in a state and an action and returns a value that determines how good, or it's meant to be a representation of how good it is to take that action at that state. So if we go back to our example here, right? If we're at a state like this, where the pendulum is pointing down, right? A good action to take would be a strong angular velocity in, I guess, either direction, or probably the direction as momentum in, right? But in in a direction so that the pendulum swings upward, right? That would be a good action to take at this not so good state, right? So that state action pair, when fed into the critic network, an ideal critic network would call that action at that state a good action to take and return a positive, or not a positive, but an encouraging value, and it's called a Q value. Yeah, and like in comparison, a bad action to take would be, if the pendulum was already upwards, a bad action would be applying a large angular velocity, right? Because that would swing the pendulum back down, right? So it's all about considering the state and the action, and the critic is trained to try to tell what actions are good to take at whichever states it's given. Yeah, and we have to consider this all inside the scope of the reinforcement learning process, right? The state, action, reward, and resulting state process. And the critic is the most influenced by this reward, right? It uses the reward as a metric on how good its predictions are. So, and with this critic, we just want to train it so that we can refine these predictions, right? Because the more accurate we can predict the best action to take at states, the better the better we can use our critic to train our actor. And the actor is trained off of the critic. And the actor, on the other hand, right, it takes in a state and it returns an action. So the critic takes in a state and an action and returns a value on how well it's doing, or how well that action is at that state. Whereas the actor takes in a state and returns an action, the best action it thinks to take at that state. And the critic informs the actor as to update to make better predictions. And once again, back to this example, right? The state given to both the critic and the actor would be probably the angle of the pendulum. It's pretty simple, probably just one variable for the angle in which the pendulum is pointing at. And once again, the action, we've went over this, right? The action is just the angular velocity applied to the pendulum. So the critic, as an input, takes in a state, the angle of the pendulum, and a given action, any action, right? Some angular velocity, and it returns how good that action is at that state, whereas the actor takes in the state, the angle of the pendulum, and returns what it thinks is the best action to take. So what it thinks the best angular velocity to give to the pendulum is. Yeah, so that's just basic, super simple overview. The one other thing that is probably really important to consider is the use of target networks. And what target networks are basically at the very start, right? When we first initially initialize the critic network and the actor network, we make duplicates of these networks. So we can call these original networks, let's say we call them our running networks, right? Our running actor and our running critic. Whereas these duplicates, these initial copies, we call them the target networks, the target actor and the target critic. Yeah, so the target actor and the target critic, these target networks, are what we use during runtime. And during every iteration of training, right, the weights that are actually updated are for the running actor and the running critic. But during every iteration, we take some of, like, a portion of the weights from the running actor and critic, and we bring them over, and to the target actor and the target critic. And the slow, movement, I guess, of like maybe just 1%, 0.1%, 2%, a very small amount of the running actor and critic weights over to the target actor and critic weights, it ensures that as our target actor and our target critic, as they evolve and they get better, they do this in a slower process. And this allows us to retain stability in the case where the running actor and critic might be, I don't know, they might be prone to updating in a non-ideal fashion, maybe, especially in this continuous control environment where there's so many unpredictabilities. But having this like slow and mediated process of actually of updating the weights of the actual target actor and critic networks that we're actually using for predictions, right? We're able to ensure that they are less volatile and they remain more stable over time. Yeah, so that's the use of the target networks. And that's just a brief overview of the entire DDPG algorithm. But yeah, we can get back to talking about how we can, use MADDPG and the extension of DDPG for multiple agents. Yeah, so now that we finished talking about DDPGs, we can start talking about MADDPGs. And yeah, let me open up the paper for this. If I remember correctly, it was written by, so people at, researchers at OpenAI and Berkeley. And MADDPG, once again, is an extension of DDPG so that multiple agents can use it at the same time. Okay, so I have thought of an example. So let's say that we have this empty rectangular shaped room, right? Rectangular shaped room, there we go. And let's say that in this room, we have 4 agents, and these agents are spherical robots. So you know those like little Sphero toys that you can like that like roll around on the ground like BB-8? Yeah. So let's say that we have 4 of those. Let's mark them as cyan. And let's also say that we have a ping pong ball or some like small ball that can roll around in the room. Let's mark that as orange. And let's say that there's some kind of X marks the spot. Can I do an X marks the spot? Let's do a star. Here we go. So the star is also initialized at a random place in the room, and the star is yellow. So this is your environment. This room is your reinforcement learning environment, and at the start of training, everything is put in a random position, randomized, right? And let's say the goal of these 4 robot agents is to move this ping pong ball onto this yellow star in the quickest amount of time as possible, right? So all of these are spheres. Spheres, they can only have, I guess, like 1 point of tangency at a time. So with all the noise and, I guess, real-world interference that goes on with rolling a ball around on the ground, it would be pretty hard for just one single agent to try to knock the ping pong ball onto the star by itself, right? And it would be even more difficult for any of these agents to do that if they were trying to like knock the ball in like different directions, right? It would be chaos. So our goal is finding a way for all 4 of these agents, to be able to work together to get this ping pong ball all the way onto the star. Yeah. And MADDPG will allow us to do this. So let's say that each of these spherical agents, let's say they have both a let's say they have a velocity. Let's say they have an x and y velocity. So they would be able to move around in an absolute form. So it's not like a car where you have like a relative steering based on where you're pointed. Instead, it's something like if you're playing a game, right, where you can steer your agent in any direction in an absolute heading that you choose. So yeah, let's give it an arrow just to indicate that this agent is able to have a horizontal velocity in the x direction and a vertical velocity in the y direction, as so far to move where it wants to move. So let's say that these velocities are limited to, it doesn't really matter, units, 0 to 1 meters per second, right? So what needs to be predicted as an action for each agent is going to be this horizontal velocity and this vertical velocity. And these are, once again, continuous values, I guess not 0 to 1, but -1 to 1, in lieu of having a magnitude, right? So -1 would be moving all the way to the left, +1 would be all the way to the right, etc., etc. And we need to do this for each one of these agents. And we need to train these agents so that they're able to work together. And this is the difficult part. Because if you think about it, right, each one of these agents, you could just say, okay, let's use DDPG and let's have a DDPG training on each one of these agents, right? And let's try to get let's try to train them at the same time maybe and get the ball onto the star. It's a naive approach. you may have a bit of success trying it, but it's not going to work well. And the issue behind this is something called non-stationary environments. And non-stationary environments basically means that if you're an agent, so let's actually label these. Let's say that this is agent A. Agent A, agent B, agent C, and agent D. Right? So let's say that you're agent A, and you're trying to learn, and the ball is like right here, right? So if we look at this as humans, we're like, okay, if agent A moves a bit up, a bit down, and then just like kicks the ball so that it rolls towards a star, it's probably like a pretty ideal course of action, right? So agent A does this. Let's say agent A takes that action, starts to go up, right? But if you're training A, B, C, and D all at the same time, right? B is going to see the state of the environment, take the state in. But then when B decides to act, A is going to have already moved, thereby changing the state. So, and even if you have all these acts simultaneously, right? Like take the state at the same time and act at the same time, the resulting state in the resulting time step is going to depend not only on the agent that just took the action. So once again, it basically means that from the point of view from any one of the agents, from the point of view from agent A, right, the environment is going to be changing in different ways that agent A can't influence or isn't influencing. And this is a key point here. And it emphasizes the fact that other things are happening in the world around any given agent that influence the environment in a way that the agent can't predict. And this makes reinforcement learning really, really difficult because agent A is trying to determine what the best action is, right? It's trying to determine maybe this is a good action or this is a good action, but it's going to be difficult to see the actual results of its actions if other things are happening around it that agent A doesn't know about, that agent A doesn't know what action B or C or D is taking. And it's going to it'll add confusion, it's going to add noise, and it's going to make training really, really difficult, if not impossible. So with MADDPG, one of the main goals is to eliminate this issue of non-stationary environments, right? Non-stationary from the point of view of any agent, right? You can see where the name comes from, because the rest of the environment isn't stationary because everyone else is moving around, while agent A is trying to make its own decision. So we're trying to eliminate the issue of non-stationary environments. And the approach that MADDPG takes to this is having something called a centralized critic. This is actually a really good graphic. We have it right here. And basically what our centralized critic is if you remember back, right, in a DDPG we have one actor, one critic. In MADDPG we have a number n actors and n critics, and n being a value of how many agents we have. So back to our example here, we would have 4 actors and 4 critics. Now, you might be wondering, okay, that's fine and dandy, right? But what do all the critics do? What's the point of all that like redundancy? So we can focus in on any one given critic. So let's go back to agent A, right? Let's talk about agent A's actor and agent A critic. So agent A's critic is something called a centralized critic, and what this means is that agent A's critic is not only going to have access to the observations of agent A, but also the observations of agents B, C, and D. To put this into other terms, it basically means that agent A's critic is not only seeing the environment, seeing the world from the point of view of agent A, it's also getting fed in all of the information that agent B, agent C, and agent D know in order to try to optimize its decision, right? And you can see this in this diagram, right? You have your observations, you have your actions, and let's say Q1 here, this is our critic for agent A. It's getting observations not only from agent A here, also agent B, and dot dot dot, agent C, agent D, agent whatever, right? So, and this is not only agent A's critic, right? Agent B's critic is getting not only agent B's observations, but also agent A, C, D. C's critic is getting all the observations, D's critic is getting all the observations. So all of these critics are getting all of the observations. And all of the observations and all of the actions. So it sees basically everything that's happening in the environment around it. And once again, our critic, right? It's our state value function. So we're trying to predict a value of how good any given state is for the agent. It's a critic's agent. And the more information we can have, the better. And the reason why we allow each critic to have information from all of the agents is because by doing this, we eliminate the issue of non-stationary environments, right? An environment would only be stationary if like, let's say for agent A, right? An environment is only going to be stationary if agent A only sees things from its own point of view. But by giving it access to the points of view of B, C, and D, agent A critic is going to know what everyone else is doing. And therefore, nothing, like no difference between different states, like state 1 and the following state, right? There's not going to be a discrepancy that isn't accounted for, because it knows where everyone else is and what everyone else is doing. So by that, we eliminate the problem of non-stationary environments. Yeah, and perhaps the other main key point to note is that in real life, it's pretty impractical to say that each agent should have all of the information from every other agent, right? In real life, it's much more likely that these agents are going to be decentralized. Decentralized meaning each agent is oblivious or independent to the whims of every other agent. Let's say that this was in real life, right? Let's say that these are agents, these are once again like little BB-8 like robots that are operating on, I don't know, Star Wars, one of the Star Wars planets, right? Like, these robots aren't going to be, they might not be able to communicate with each other for whatever reason. So, knowing only what they know themselves, they still have to try to work together and cooperate to achieve their goals. Now, this doesn't mean that the agents are completely don't know what's going on in the world, right? They're able to make their own observations. So, from their point of view, they might be able to still see or locate where the other agents are, right? And that would be considered their own observation. But when we talk about decentralizing these agents, it only means not giving A access to B, C, and D's point of view. So A still might know where B, C, and D are from GPS, radar, LiDAR, whatever, but they just won't have access to B, C, and D's own observations. Whereas, once again, in the centralized critic training process, it does. So, the solution to this, at least, the solution to not, to like this like real-world dilemma of our agents not being allowed, or not being practical for the agents to have their own, for the agents to have everyone else's observations, the solution to this is something called centralized training and decentralized execution. Once again, it's perfectly alluded to in this diagram. And what we can see here is you can see this green box, this green outline, and this red outline. And the green represents information during training, and red represents information during execution. So if we go over these parts, so we've talked about the Qs here, right? The Q values. These are your critic networks. Observations, O, actions, A, pretty self-explanatory. And this is for each agent, so dot dot dot, so agent 1, agent 2, 3, 4, 5, etc. And pi here, pi stands for policy. Policy being your actor network, right? As you can see by the diagram, the actor takes in the observations and outputs an action, right? So once again, our goal is for during execution, when we're trying to run this when we're trying to run a program in real life. We want all of our agents, all of our individual actors, to be independent of observations from everyone else, which means we cut them off from their critics, right? And if you think about it, after our actors have been trained, right, trained using the critics, there's really no use for the critic anymore. Because if you remember, right, the actor takes in a state and it outputs an action, right? The only reason that we use a critic is for training the actor initially. But if the actor is already trained, it has access to a state, it can observe things, and its output is an action, right, which is what it needs to do. So there's no use for the critic, because the critic is only useful during training. So when we do decide to get out of the training phase and start actually using our algorithm, right, we don't need these critics, and therefore we cut out the need for the observations for every other agent. That's what makes MADDPG a centralized training, yet decentralized execution. Which once again is really, really powerful, because during training, right, if we're operating in a known environment, in something that's like controlled, regulated, something that that I guess like scientists can test out beforehand, right? It's easy to train these agents. It's easy to give each agent access to everyone else's observations. Yet, if we're ever trying to implement it and we have our agents already trained, they're good to go without knowledge of what everyone else is doing. Yeah. So by the sense, we can just quickly go over the pseudocode for the MADDPG algorithm. Should be down here somewhere. Right here. If you can see, compare it to this. It's really simple. Sorry, not really simple. It's really comparable to the DDPG algorithm, and you can see it updates each actor, it updates each critic. You have also using target networks once again, since it's an extension basically of DDPG. The main difference once again is just the fact that each critic is getting information from everybody. Oh, one thing that I forgot to mention previously was the reason that we have a critic for every single agent. So yeah, you might be wondering, if each critic, right, is training on the observations of every other agent, why do we need to have like one critic per agent? Why not just have one critic for all the agents, right? And this is a very fair point. The reason why that we have each agent have its own critic is because our agents are not necessarily homogeneous. In this example, yes, each agent is homogeneous in the sense that all of these agents are the same. They have the same capabilities. They are the same, right? But there are cases where they might not be the same. There are cases where Agent A might be twice as fast as Agent B, C, and D, or Agent C might be able to teleport to other places in the room. I don't know, something crazy like that, right? But in the case where the agents are not homogeneous and have different capabilities, this is where having multiple critics comes into play, because while having one critic will work for homogeneous agents because all your agents have the same capabilities, if you have non-homogeneous agents and you want your agents to be able to utilize their own capabilities to the greatest extent, having many critics will allow you to do this, because each critic can be customized can be trained, I guess, in a customized fashion to the capabilities of each agent. Yeah, and it's kind of like in real life, where you have people working on a team, right? Everyone has their own strengths and their own weaknesses. And in this case, right, with your multiple agents that are working together to try to solve a goal in the most efficient way possible, you're going to want to use, if your agents are not homogeneous, and if your agents have different kinds of like capabilities, right? You want each agent to be able to utilize their own capabilities to help the entire team solve the problem in the best way they can. Yeah. Yeah, and just to wrap everything up, right? This can be applied to so many different things. Basically any problem where you have numerous agents that are trying to work together to solve one single goal, usually you can apply MADDPG to it. Yeah, so with that said, I will link both of these papers, I encourage you to read them yourselves. They're pretty dense, and definitely more than we could thoroughly go over in one lecture. But hopefully this lecture was informing, I guess, of this really cool algorithm that has so many different applications in different like multi-agent processes, scenarios, problems, right, that we want to solve. Um, but yeah, thank you for listening. This has been the advanced lecture for TJML Club. Yeah, thank you. Hope you have a good week. Yeah. Goodbye.